Welcome to day 13, or should I say night 13 of the Advent of Code. Today is all about catching departing buses. Let's see. So let's pretend that every 7 minutes, starting at midnight, one bus departs, the next one every 13 minutes, the next one every 59 minutes, and so on. And we want to catch a bus 939 minutes after midnight. Which of these is the first one that will depart and that we will catch? That's the question for part 1. And I thought about this with some nicer numbers. So let's say we want to depart 100 minutes after midnight and a bus departs every 30 minutes. I think that's easier to visualize in your head or calculate in your head. So if you simply compute 100 mod 30, then we get 10 minutes ago we missed our bus, and the next one will depart 30 minutes minus those 10 minutes, so in 20 minutes. Okay, so we basically want to minimize this number. Okay, I already prepared some boilerplate code here. So for example, the earliest is the 939 from line 10. That's when we want to depart. And the bus IDs is just a sequence of those numbers, 7, 13, 59, and so on. Okay, so we have to compute the same stuff as in lines 20 and 21, just for all the bus IDs. So let's start with the bus IDs and then map a function over them. So a function over one bus ID. And then let's return a vector where the bus ID is the second element and the first element is that calculation, right? So that would be bus ID, so the 30 in line 21 minus the modulus of earliest and bus ID. That's the calculation in line 20. Okay, so how does this look? Yeah, so we can see the bus with the ID 7 will leave in 6 minutes, bus 13 in 10 minutes, bus 59 in 5 minutes, and so on. And this is the next bus that's going to depart. Okay, so we would like to see the minimum value according to the first element of those pairs. And we can use the min key function for that. I had to Google a bit to find it. Because at first glance it doesn't look like you can use it with vectors. It looks like you can only use it with maps. But if you look at the implementation, so this is overloaded for as many arguments as you want. Let's look at the 2-arity version. Then k is simply applied to both arguments, and then we check which one is smaller. Okay, so we could simply use the first function first, which for a vector gives us the first element. Okay, and then we need to apply the min function at first to our vector of vectors. Okay, so somewhere I forgot a parent. Let's see. Okay, so like here. Yeah, okay, so 5 and 59. That's looking good. Okay, cool. Now, according to the puzzle, we have to multiply those two numbers. So we could destructure that and then multiply a times b and so on. But what would be even simpler is to simply apply the multiplication function. Then we will choose the 2-arity version. That would be this one, which directly calls Java interop. Okay, and then we get 295. Okay, and for the real input, what do we get? We get 3600. Yeah, that's also correct. Okay, so I think with a simple example, this is achievable. Okay, so maybe, I don't know, half an hour or something. Okay, so part 2 was a lot harder for me. I spent several hours understanding it and then finding an efficient solution because brute force simply doesn't work. But first of all, what are the semantics of the input now? So the first number is ignored. It doesn't have any meaning for part 2. And then again, a bus departs every 7 minutes, 30 minutes, 59 minutes, and so on. But now the indices matter here. So we're trying to find a point in time, some minutes after midnight, where the 7 bus immediately departs, and then 1 minute later the 13th bus departs, and then another minute later and another minute later, it doesn't matter if buses depart, and then another minute later the 59 departs, and 2 minutes later the 31 departs, and 1 minute later the 19 departs. Okay, and again, you can't just use Bruce Ford. I tried it. Bruce Force, it doesn't work. Okay, so if you play around a bit with the first two buses, sooner or later you will realize that the number 77 looks good because it evenly divides or is evenly divided by 7, and the next one 1 minute later is evenly divided by 13. Okay, and we could ask what is the next number after 77 which also satisfies these equations, and if you think about it a bit, that would be 77 plus 7 times 13, because as a general rule, a plus b is divisible by 7 if both a and b are divisible by 7. Right? And this number is divisible by 7, namely 13 times. And this number is divisible by 13, namely 7 times. And we can add it again and again and again, and sooner or later you will find the number 350, which also has the property that if you add 4 to it, then it is divisible by 59, and that's interesting because here at index 4 we have the 59. Okay, and then again, you can add 7 times 13 times 59 to it an arbitrary amount of times, because this number is divisible by 7 that many times, by 13 7 times 59, and by 59 that many times. Okay, and then you get the next number, and then we repeat this game. Okay, so I formulated an algorithm in some pseudocode or pseudocode. So we start with the sum equals 0, and then we keep adding 7 until sum plus 1 is divisible by 13. That's how we found the 77. And then we keep adding 7 times 13 until sum plus 4 is divisible by 59. That's how we found the 350, and so on and so on. Okay, and I call this variable the sum, as you can already see. Then here we have a product, which is comprised of prime numbers. Here is our index that's added to the sum, and these numbers are all prime numbers. I guess this is important for the puzzle. Okay, cool. So let's write a function that does exactly this, that performs one of those lines in the pseudocode. I call it magic. I simply couldn't find a better name, and it seems like magic if you look how few lines of code it actually is. Okay, so what do we want it to do? We pass it two pairs, where the first pair consists of the sum so far and the product so far, and the second pair consists of the index and the prime. Okay, and then we want to output the next sum and product for the next iteration, for the next line, basically. Okay, cool. So how would we start? Maybe with a loop recur. We want to be very efficient, and this is a common idiom that simply says I want to have a local binding called sum that shadows the parameter sum. So we use the parameter as the initial value, and then later we will provide new values for that local binding. Okay, cool. So maybe let's first check if we already reached the 0 with our modulus calculation of sum and index. So plus sum index is this part of our idea here. Then the mod is this part. Oh, I forgot to provide the prime. Right? Mod prime is this part. And yeah, if the mod is 0, that means it is divisible. Okay, so if that is the case, what do we want to do? We want to return the new vector, so that would be the updated sum, and then the product grows by the prime. Right? That's basically the times 13 here, or the times 59, or the times 31. Okay, so that's that, and otherwise we have to recur and try the next value of sum, which is sum plus product. Right? Keep adding 7, and later keep adding 7 times 13, and so on. Okay, so that would be that. So let's see if that works. So we call the magic function with our example input here, and we get 350. That's correct. And 5369, I think, is also correct. Let's see, what's 7 times 13 times 59? Is it 5369? Yeah, okay. So that already works. So typing this in only takes 5 minutes, but it took me several hours to get there, mentally or theoretically. Okay, cool. So this works now. So what's the boilerplate that we provided here? Yeah, so I cut off the first element because it's not really interesting for the part 2. And now we have to associate those strings with indices. And we can do that by interleaving our sequence with the second sequence, in our case, the range function. Okay, so we interleave a finite sequence of strings with an infinite sequence of numbers, and then once the finite sequence ends, then the interleaved sequence also ends. Okay, and then I want to look at those in pairs. We also know the partition function from previous videos, and the step is 2. That's why I don't have to provide it. Doesn't make a difference. Okay, cool. Now let's maybe parse those numbers. So let's say we want to map with a function that structures the pairs and says index and prime. And then we have to check that the prime is not just the number x, right? So we can say if not just, whoops, not just the string x, our prime. Yeah, that's looking good. Then let's return another vector where the index is not changed and the prime is parsed with parse int. Okay, so let's step out of map. Yeah, that's looking good. Unmatched delimiter. Okay, so this is not correct. Yeah, okay. Okay, so now we can see the normal pairs, the strings were converted into integers, and the pairs where an x was used instead of the number. Now we have nils, and we can get rid of those nils by simply saying, oh, let me see. What did I do wrong? Here I'm in the map function, and now I'm not inside the map function. Okay. We can simply remove all the elements that satisfy the nil predicate, right? Just so we can see the difference here. The nils are still present, and now the nils are removed, and remove is just the opposite of filter. You can see it simply delegates to filter and complements the predicate, so turns the result of the predicate around. Okay, nil is just a function that checks for nil. That's probably just Java interrupt, right? Yeah, just Java interrupt. Okay. So that's our sequence now, and then we can reduce with our magic function. And normally we provide f, val, and col, where col is provided by the thread last operator, but you can also leave the initial value out. Then the first call to f will use the first 2 elements here. That should also work. So in our case, the magic function. Yeah, and then we get the number, what is that, 1,068,781. That's correct for the demo input, and the second number is not really interesting to us, so let's ignore it. And then let's look at large. Yeah, and that's quite efficient. So again, doesn't work with brute force. Okay, cool. So I think that was quite exhausting, but still, let's see if we saw something interesting today from a Clojure perspective. Yeah, so the mod function isn't used every day. That's basically the % in Java. Good to know how to spell it. Then the min key function was new, probably when you try to sort a vector of or a sequence of maps, then this will come in handy. And then the apply function. Oh, will this also work with reduce, by the way? Yeah, cool. So many times it doesn't matter if you use apply or reduce, because reducing, let's do it like here. If we say reduce with times 2, 3, 5, this will do exactly what we want. So the first call to times will pass 2 and 3, that's 6, and 6 times 5 is 30. If we only provide 2, that will work. For a single argument it works, it simply returns the single argument, and if there's nothing, then the identity is returned. Right? So we can simply ask the times function, what is your identity, and that will work. Okay, cool. So that's also sometimes useful. Then a lot of math theory. Okay, then the 0 function is probably a bit more efficient than explicitly comparing to 0 with the equals 0. Then again, the mod, but the rest is just good old arithmetic and some loop recur. Okay, then the interleave function is quite useful. It's often used in conjunction with infinite sequences. But of course, if you interleave two infinite sequences, you still have to be careful as always. Okay. Yeah, and then I think the remove nil is a nice idiom. So if you only provide if with a single clause here and not just a then clause, not an else clause, then we have an implicit nil in the else. And then we can remove that here with the nil predicate and the remove, which is just the complement of filter. Okay. I'm already 4 hours late. I think I'm going to end this here. See you next time.